Welcome back, students. We have discussed interference, and now we are going to start something called as diffraction. This is again a wave phenomenon. It happens with sound waves, water waves, and also with light waves, and any other wave that you can think of will have to undergo this process. Just like interference, there will also be a diffraction of waves. But what is diffraction first? Well, it is called as the bending of the wave. Okay, in optics, it will be called as a bending of light. The light looks like it's bent around small apertures and obstacles. Aperture is an opening, and obstacle, as you know, is a block. For example, to illustrate it, I'll take a point source, and let us suppose that there is an opening here. And then I have a screen here. So generally what you expect to happen? Well, you expect the light to go through this aperture, the small opening. And as it travels in a straight line, you would expect it to go in and hit you. So this is your source. This is your aperture, and this is the screen. Okay, and say wall. So the source sends light, goes through this, and then it goes and hits the wall. So if it is an opening, then it should travel in a straight line. But what actually happens is that instead of what you expect is everything else is dark. Okay, here you expect this to be dark. Beyond this should be dark, and this should be bright. What actually happens is that light does not hit here, it is actually do something like this. So instead of seeing this as bright, you also see this as bright. Okay, so now I'll do this way. Instead of light hitting here as a straight line, now you have bright here up till here, and the darkness starts only after this. So this also becomes bright. It's an extra bright. Okay? See, this is bright, and this is also bright, and everything else is dark. You would have expected the brightness to be only here, but then the brightness is extended to other regions too. Slightly more. So now the light looks like instead of going straight, it looks like it is bent. So diffraction is a bending of light. This for an aperture, an opening. What if I have an obstacle? Again, if I have an obstacle, an opaque thing, then I have the source here. So light, you don't expect light to. You would expect the darkness to be here. Okay. So this should be dark for you if you extend this, and this should be bright, and this should be bright also. But what actually happens is that light kind of bends inwards, and then it goes like that. So what happens is only here you have dark, and then you have brightness here. Only this part is dark, only this is dark. Yeah. And from then on you get brightness. Likewise here you get dark here, then you get dark here, but you get brightness here. So light seems to bend doesn't seem to travel in a straight line, it seems to bend around small apertures and obstacles. This phenomenon is called as diffraction. And why does it happen? Well, it happens because light is not a particle, because it's a wave. You can imagine this for the most part. If you think about it, light will start, so your light starts hitting here as a wave. Okay? And what happens is, like, from here, then to that, you see the wave is expanding. Again, here also the wave will extend. So it doesn't stop there. There is this extension. Because it's a wave, it's not a particle. It's a wave, so you get that. Likewise here also, light comes and hits here, and like this. Okay? Wave. It moves kind of like a wave, so you get this. Okay, but a proper study of this is done. Intuitively you can understand this like this, but then the proper study is not this. Okay. First of all, diffraction is the apparent bending of light. That is diffraction around small apertures and small obstacles. Okay. But why does this happen? This happens because of lots and lots of interference. We studied interference for two waves, but diffraction is interference at a large scale, not just two waves interfering, but millions of waves interfering. If millions of waves are interfering, then clearly you are going to have a diffraction pattern. So that's the I should say, the millions of waves are interfering, you will have interference patterns for all these waves, and that interference pattern becomes the diffraction pattern. So that is why you feel that light is bent around the edges of apertures. Let us study about diffraction from the fundamentals. Let me take a small opening, and then there is also a source which sends light through that opening. So this is going to be my opening. So I have a source of light. Okay, let's say I have some kind of a plane wave reaching here. The source, then the wave is reaching here. And what happens is that here you take this opening. Per wave theory, each point on a wavefront acts as a secondary source and produces its own wavelet. So you see here, if it's a small opening, then each point on that is going to behave like a point, a secondary source of light. So this will produce a wave, next will produce a wave, then third will produce a wave, fourth will produce a wave. So if you have, I don't know, a trillion points there, or a million points there, then all of them will produce their own waves, basically. And all of them will interfere. So if I take a point in space here, let's say, let me randomly take a point here. This is a random point. So this wave will reach there, this wave will reach there, this wave will reach there, so will reach there. Likewise, millions of waves will reach that point. And any other point. This is P, and I can have a Q here, I can have an R here, and all these points will have light coming from those sources. Okay. So at this point, the value of light would be the sum of all of them. all of the contribution from each wave would be summed up, and you would see the value of light there, light intensity. This can be bright, this can be dark, this can be somewhere in between. So anything could happen. And what should you do? How do you determine? How do you decide? How do you predict what would be the value of light at this point when millions of waves interfere? So you have a small opening, all right, but then you see that this small opening can have millions of points. From each point you can have waves coming and interfering at a particular position in space. Okay. So then what would be the value? What would be the intensity of light over here? That's what you are going to see. Okay. So what I am going to do here is that I am going to keep the screen far away. If I keep it far away, then I can say that these lines are almost parallel. Okay. So the wave from this point, let's call it as A, and I'll call this as B. The wave from this point, this line will be parallel to this line, and then to this line and this line, if I keep this screen sufficiently far from the source. Well, we'll consider a case like that. In that case, what happens is this. So you have a line, okay, this goes to P, and this also goes there, be parallel. Parallel, like that. All these waves go and meet at a far off point, nearly parallel. And let me also take, okay, it's understood that light comes here, light hits here, okay, so it's understood. So light comes and hits here, blocked here, only this light will go. Let us suppose that the length is A. That's the width of the slit. This is the width of the slit. So we have a parallel line there. And if a parallel line, then if you take this, line, and this will make an angle theta, and this will also make an angle theta with another thing here, and next everything will make an angle theta with a horizontal line like that. I've taken some random point P. Okay, so now how can I predict what would be the value or the intensity of light here? I don't know. What do I know? I know that if two waves interfere with a phase difference of 0, then it will be bright. So the point will be bright. If the path difference between them, the two waves, is lambda, then it will be bright. So lambda or n lambda, multiples of lambda. It will be an integer multiple of lambda will give you a bright spot if there are only two waves involved. Okay, let me take this wave and then this wave. But there are millions of waves here. I can't just take two waves. There are millions of waves, right? So all of them are going to interfere there. So it is not just two waves. Right? lots of them are going to interfere. So how do we decide? It's going to be really complex. How do we know the phase that each one will contribute at every point? It's going to be really, really complex. Because we find it difficult to do even for two waves, and now we're talking about millions of waves interfering, and y would be equal to, see, like we want to find y, then y is going to be equal to y1 plus y2 plus y3 plus maybe y 1 million. I don't know. All this, the sum of all that would be intensity, right? So it will be very tough for me to do. But is there a smarter way of doing it? Can I predict what might happen? Okay. Let's put it this way. If so this is line, and this is also parallel. Line parallel to that. Well, if I drop a perpendicular like this here to these two, okay, then notice here from this point onwards, the path length will be the same. From A, at this I'll call this as C. This point is C. From A to P will be the same as C to P. Because from that point, the path length will be the same, parallel. Then what's the path difference between this wave and this wave? It's going to be BC. So BC is the path difference between the first wave and then the last wave. So what's the path difference between the first wave and the last wave? That's AP. First of all, BP minus AP. BP minus AP, which is equal to BC. So what is this path difference? Well, think about it. This is theta. Okay, you know that this is 90 degrees, and let's draw it straightly, in extended form. Parallel like this, then I drop here. Okay. This is what we have done. This is A, this is B, and this is C, and this is 90. Parallel. This goes to P, and this also goes to P. This is what we got. So this we know is theta. If this is theta, what does it? This is 90, right? So this is 90, and this must be 90 minus theta. Yeah. This side will, and this is 90. Since this is 90, it's 90 minus theta. This must be theta. So this is theta. If this is theta, and this will also be theta. And we also know that this length is A, width, right? So the width of the aperture, that is A. But what do we want? I want BC. Then how do I find BC? BC can be expressed in terms of A and theta, right? So if I take this triangle ABC, then I can express sine theta as BC by AB. BC by AB. So BC by AB. But AB is A, so BC is equal to A sine theta. So the path difference between the first wave and then the last wave here is actually A sine theta. Okay, but what do you expect to happen here? Well, if this wave, the first wave and then the last wave, they interfere, and if this BC is n lambda, let's say A sine theta is n lambda. I'm talking about this is wave 1 and this is wave 1 million. I'm talking about just two waves. wave 1 and then wave 1 million. When they interfere, A sin theta is BC, and that must be equal to, if it is equal to lambda, n lambda, 1 lambda, 2 lambda, 3 lambda, whatever, n lambda, then these two will interfere constructively. So if these two are the only waves, then you can expect a bright spot there. But unfortunately, these two are not the only waves. We have, out of this 1 million waves, just remove 2, then you have 1 million minus 2 waves. It's 9,99,998 waves are there. They also come to the same position. So they will also interfere. So it's a tricky situation now. I want you to pay attention. I want you to follow me closely, because most people don't understand this idea. They get confused. That is why I want you to follow me. I have two waves. I consider just two waves now. The first wave and then the last wave. Out of a million waves, consider only two of them. And then I find the path lengths to be n lambda between the first and the last. At a particular point P, the path difference between these two waves is n lambda. And if these two are the only waves that interfere, then I will get a bright spot. But these two are not the only waves. There are other, in our example, 9,99,998 waves, which also interfere with these waves. So what do you get? You don't know. Then I have to be finding the contribution of each and every wave to even know whether it is going to be right or not. So I'm going to take a slightly different approach, okay? A smarter approach. I'm not going to calculate everything, but I can figure out something from this arrangement. Let's see. Well, let me come back to this. I said this path difference, let's say this is lambda. This is lambda. I'll just take 1 lambda. If this is 1 lambda, at the midpoint, if we take this one, the path difference between this wave and the first wave is going to be lambda by 2. Well, think about it. I have this wave, and 9,99,999 waves will interfere with this wave at point P. But now I'm going to take this wave first and then the middle wave. Okay. If the path difference between the first wave and then the last wave is lambda, then the path difference between the first wave and then this wave at the off position, that would be lambda by 2. But what happens when these two interfere? When this wave interferes with this wave, then it cancels this out, because there's going to be a destructive interference between this wave and this wave. I'll call probably this wave as D. The wave at D will interfere with wave at A, and both of them will be destroyed. So if these two are destroyed, what will this interfere with? If this was not there, yes, now B can interfere with A. But if this is present, wave D, if this is present, then what happens now? The wave that starts from A will be cancelled by the wave that starts from D. They destroy. And what will this interfere with when there is no wave? If this contributes plus 5, and let's say this also contributes plus 5, but if this contributes minus 5, then what happens? This cancels. You don't get 5 plus 5, 10. You get 5 minus 5, 0, now it's left alone. It's like that. Okay? So, this is what I want you to understand. So what I'm going to do is I'm going to divide this A and this length A into two parts. One part above D, the other part below D. Okay, easily figure things out now. So, if the path difference between the first wave and then the millionth wave is lambda, then the path difference between the first wave and then half a million plus 1th wave will be lambda by 2. So, this wave will be cancelled by this wave at half the distance. So, clearly, the next wave will be cancelled by the wave next to it, because these two will also have lambda by 2. And then the third wave will be cancelled by the third wave. Gone. So likewise, all the waves which are above D, will be cancelled by all the waves which are below D, because you have divided this into two parts. Cancel. So what do you get here? You will get a dark spot. There will be no light, because light from one is cancelled by light from another. So the top half will be cancelled by the bottom half. So everything will be cancelled. So you will have a dark spot there. This is where will be a dark spot. So surprisingly, this equation, which you may intuitively expect to be bright, is actually dark. Why do you expect it to be bright? Because in your mind, you are thinking about the interference of just two waves. If there are only two waves, and the path difference between these two waves is lambda, then clearly you will get a bright spot. But those are not the two waves. There are millions of waves between them. They all interfere. They all put their own value there. So it's like in a class, some people come and give some money and somebody else takes the money away. And somebody comes and puts 10 rupees and somebody takes 5 rupees out of it, leaves 5 rupees there. And somebody comes and takes 2 rupees. Or somebody comes and puts 1 rupee. So it's like that, the class full of people, some of them put money randomly and some of them take money randomly. If that happens, then you can never say how much money would be left there. If everybody is contributing 10 rupees, then you can say, yeah, if I have a class of 20 people, then I have 250 rupees at the end of it. But if you don't know whether someone is going to contribute or take money, and you don't even know the amount, you are not very certain about the amount that each person is going to contribute, then you cannot predict it. Okay? You have to keep that in mind. And that is why we are arriving at a case where whatever is put in is taken away. It is something like this. The contribution from one wave will be cancelled completely by the wave here. So is what will happen. You will get a dot spot there. So when there is an interference of just two waves, when it's n lambda, you will get a bright spot. If there is an interference of many waves, and you have no idea what you're going to get, and the path difference between the first and the last of these million waves, I'm ignoring all the other waves, I'm just taking the first wave and then the last wave. If the path difference between these two waves is n lambda, then all these waves, you can have 1,000 waves, million waves, 2 million waves, or 2 billion waves, doesn't matter. If the path difference between the first and the last is n lambda, then you are going to, all these waves are going to cancel each other, and then you are going to get a dot spot. So don't think that light is behaving weird in the case of diffraction. It is behaving the same way it was behaving with interference. But in interference, we are just two waves. So it was very easy for you to predict. But in diffraction, you have many waves. A large scale interference is diffraction. And that happens when the path difference between the first and then the last wave is n lambda, then you will get a dot spot, not a bright spot. I want you to understand that. Well, okay. Then what happens if this is instead of lambda, you have 2 lambda? I said this, right? Okay. Instead of lambda, I have 2 lambda. This is 2 lambda. Then what happens? If it is 2 lambda, the first one, this A and D, will have lambda. So they will contribute. Again, you are in trouble. Right? These two will constructively interfere if the path difference is 2 lambda. Again, you are going to do the same thing here. Well, then you divide this into 2 more parts. Clearly, this wave now will be cancelled by this wave will be cancelled by this wave will be cancelled by this wave. So, the first quarter will be cancelled by the second quarter, and then the third quarter will be cancelled by the fourth quarter. So that's for 2 lambda. If it's 3 lambda, again you have to divide it into 6 parts now. There's 1 lambda, you divide it into 2 parts. It's 2 lambda, you divide it into 4 parts now. If it is 3 lambda, then you divide it into 6 parts, and it goes on like that. So for n lambda, the path difference is 1 lambda, 2 lambda, 3 lambda, 4 lambda, 10 lambda, 100 lambda, whatever it is, you will get a dot spot all the time. I want you to understand this. I can even simplify this. If theta is small, then I can say that sine theta, if theta is small, I can go for the small angle approximation and then say sine theta is equal to theta in radians. So that gives me A theta is approximately equal to n lambda. So theta can be written as n lambda by A. So if this is lambda, if P, if you take P, and the path difference between the first and then the last wave is lambda, then I'll get a dot spot. And then if I take another point Q somewhere here, then if I take the, let's say now I'm going to have a different, right? So it's going to be like this. I'll use a different color. goes there, around far away. Parallel. Okay. So take this. Q is also far away, so all lines are parallel. So now if we take this, I'll have a different angle. Okay, and what that angle will be? So it will be 2 theta from this expression. If this is in 2 lambda, okay, it is lambda. So the special cases will be theta 1 is equal to, you can have lambda by a, and then theta 2 can be equal to lambda 2 lambda by a, and then theta 3 can be equal to 3 lambda by a, and so on. So you notice here, all these points will be dot. This is dot, and next thing will also be dot. So you can see this. The angle between, the difference between, the angular difference between P and Q, right? I can say that the angle between P and Q, if you think about it, then that would be theta. So that is, you will have dot spot here, dot spot here, and dot spot there. So if you look at the path differences, it will be lambda, then 2 lambda, 3 lambda, 4 lambda. For all of them, you will get dot spots. Okay. Now we can think about it. So dot to dot, and clearly you will have other values here, right? Non-zero values, non-dot values. So what should have? So you will have light here. So from dot, it will become bright, and then it will again become dark. So this would be the fringe width, or you can say the fringe angle. This is because keeping it very long. You can either find the fringe width or the fringe angle. Either can be found using this. But how do you find where you are going to get the bright spot? Well, you can do this. Where are you going to find the bright spot? Clearly, the central one here, the central one must be bright. Why? Because there will be no path difference at all. All of them will go straight, right? Here. All of them will go to that point. That will be bright. But we'll do a mathematically more convincing proof of all this. Now let's take this case. That's a point P, a random point again. But then the path difference BC between the first wave and the last wave is not lambda, but it is actually 1.5 lambda. 1.5 lambda or 3 by 2 lambda. Let's see what's going to happen now. What will happen here? Well, this point, if we just take these two waves, because if these two waves alone were to interfere, then the path difference is 1.5 lambda, 3 by 2 lambda. Then the phase difference will be 180 degrees, and you will expect a dot spot. If the interference is between only these two waves. But as we have been seeing, that the interference at this point P will not happen only due to these two waves, but due to all the other waves too. Everything will be involved. Then how do you approach it? The same way we did for the lambda case. We'll do the same thing for 3 by 2 lambda case. So what I'm going to do, if this is 1.5 lambda or 3 by 2 lambda, then if I divide this into 3 parts, okay, that's like this. If this is 1.5 lambda, and what would I get? This will be 1 lambda, 1.5 lambda, and this would be 0.5 lambda. A lambda by 2, then lambda, I'll do this way. It's going to be lambda by 2, this will be lambda, and this is going to be 3 by 2 lambda or 1.5 lambda. Okay. So now what can you expect here? You see, this wave will be cancelled by this wave, and this wave will be cancelled by this wave, because they will all have lambda by 2 difference. So one part will be cancelled, the top part, let's say, is cancelled by the bottom part. Then what are you left with? You are left with this set of waves. This is what I'm doing now. This set of waves. They don't have a counterpart to cancel. So they will contribute to light. Their contribution is not taken away. So whatever this wave contributes is going to be there, and this wave contributes is going to be there. So it's not going to be cancelled by anything else. But what this contributes is cancelled by this. What this contributes is cancelled by this, because the phase difference is lambda by 2. But here this is not so. For all the waves like beyond lambda and till 1.5 lambda, they are not going to be fully, they are not going to be cancelled at all, totally cancelled at all. So these will contribute to brightness. So you will get a bright spot. So as we found out in the previous case, in this case also, non-intuitively, you will find a bright spot, when the path difference between the first wave and the last wave is 1.5 lambda. Okay? So if this is a lambda point, and for a point somewhere here, we will get a really bright spot. Okay. So again, for bright spot, you need to get A sine theta is equal to 2n, or I'll say n plus half lambda, or 2n plus 1 by 2 lambda. If this condition is met, then you will find a bright spot. So even though you cannot mathematically compute the interference for all these waves, millions of waves, thousands of waves, you don't even know how many waves are going to be there. Even though you don't get into a rigorous mathematical calculation of what will happen there, you can still arrive at the right answer by looking at this problem slightly differently, a little smartly. Because you know that if you divide this like this, then 2 will cancel, then you'll be left with this, which will not be. So that's for 1.5. What if this is 2.5? Well, if it's 2.5, then what should you do? Then you should divide this into 5 parts. Here, you divide that into 3 parts. Then if it's 2.5, 5 parts. It's like this. If 3 by 2, 3 parts. If it's 5 by 2, which is 2.5, and divide it into 5 parts. If it's 3.5, which is 7 by 2, then you divide that into 7 parts. If you divide that into 7 parts, what do you understand? One part will be cancelled by the second. So the first is cancelled by the second, then the third is cancelled by the fourth, and fifth will remain. Okay? So this is for 2.5. For 3.5, Again, we are going to have 7 parts. First will be cancelled by second, third will be cancelled by fourth, fifth will be cancelled by sixth, then you will be left with the 7th part. That would not be cancelled by anything. So you will have a bright spot there also. But what happens is, notice here the contribution is from 1/3 of the slot. Okay? You have this opening, 1/3 of the length contribute. All these waves contribute to brightness. But when you divide it into 5 parts, in the case of 2.5 lambda, then only 1/5 is contributing to brightness. And if you divide it into 7 parts, then only 1/7 is contributing to brightness. So as you go farther away, then the intensity will come down. Okay? So if this is, let's say, if this is dark, as we saw, because it was lambda, right? Okay, and this was bright, because it was 1.5 lambda, and this is 2 lambda, this is dark again, 2 lambda, and then we'll get some other point that would be dark again, sorry, bright again, but then it will be less bright than this point. The other point, as you go farther away, the brightness reduces because the contribution of light is getting reduced as you go farther and farther away. Because the angle becomes bigger and bigger, and only when the angle becomes bigger can the lambda change. So, as you go farther away from the central brightness, as we just discussed, okay, the brightness decreases. So likewise, as you've done for the positive y-axis, if you do the same thing for the negative y-axis here, then what are you going to get? You're going to get a point again here, let's say P dash, where you're going to get a dark point, and that would be lambda here, right? So here you have a dark point, and then here you have another dark point, and this is also a dark point, and this is going to be bright. And again, if you go to another point here, then Q dash, and that would also be a dark point where you have 2 lambda this way. So what happens is something like this. So you have a dark point here, and you have a dark point here, then you have a bright point here. So you can see this is going to be the bright fringe. You can see that. This will be the brightest, and then because we told you at the center, all the path difference for all the waves will be 0, because we take the central lines which go straight. Okay? The path difference will be 0, so they will all contribute. There is no distraction that will happen here. So you will have maximum brightness here at the center, and then the brightness will come down and become dark here, and then dark here, and again from here to the next dark point, you will have something like this. Okay? So the brightness will increase, it will become maximum when you have this condition, the 1.5 lambda condition, and then you will have then become minimum there, and likewise you will also have this from PD dash to QD dash. You will have a bright spot here. So even though I've drawn it like this, no, you're not going to get bumps there. This is just a measure of intensity. When you draw it like this, you're going to have, what I'm saying is, you're going to have the maximum intensity at the center, and then the intensity will go down, become dark, then intensity will increase, and then become dark, like that. But look at the width. You see, the central fringe is what you call as the central maximum. The central maxima. And this is the first maximum and second maximum, stuff like that. Then this is the first maximum from there. So this is central maxima. If you look at the width of the central fringe, it is actually double. You can see that. If this is theta, you have theta here, you have lunar theta here, so it's double. So the central fringe is the widest, and then you have the smaller ones with decreasing intensity. Each will have decreasing intensity there. So you can see that. So this is the diffraction pattern. So this is what is happening. So what you need to understand to summarize the whole thing is this. Interference is between two waves and diffraction is between many waves. So that's about it. To summarize, interference is between just two waves and diffraction happens among lots of waves. When lots of waves interfere with each other, then you get diffraction. Lots meaning 1,000, million, more than a million, whatever. So this is, and when that happens, you will get a central maximum, and after that, you will have the first, second, third maximum. And the central maximum will be the widest with 2 theta angle. It's wide. I want you to understand. The double slit experiment is actually a superposition of 2 single slit diffraction patterns. Okay, you get a diffraction pattern from one slit and then get a diffraction pattern from the other slit. Then when you superpose both of them, then you will get the double slit interference pattern. So like you will have something like this. Okay, you can see that, and you will get this is actually the fringe width of the interference. So this is the interference pattern you get in double slit. Again, like it will extend like this, and then this will be less bright, so you won't get a lot of them. I mean, you're not even get to see too many of them. Even if you do, then they won't be that bright. But here you can clearly see that the superposition of 2 single slit experiments will give you this pattern. We'll do a problem now. Example problem 10.5, but then it refers to example 10.3. So let me read the problem first and then we'll go ahead. In example 10.3, what should the width of each slit be to obtain 10 maxima of the double slit pattern within the central maxima of the single slit pattern? Well, in example 10.3, we were given these values. D is the distance of separation between the slits, and then lambda, and then D is the distance between the slits and then the screen. Using these values, we calculated beta to be 0.5 millimeter. That's what we did in example 10.3. So it's like this. You have 2 slits and then you have screen there. So D was given and then D was given, and then you started observing these patterns. Yeah, it's like that. That's what is happening. And this one, for example, this is the bandwidth, 0.5 millimeter. So this, if you are going to use a single slit, all this will have to be accommodated in the central maximum. So if you had used a single slit, notice that there would be a central maximum, then you have to accommodate 10 of them in this. So the central maxima, if you remember, this is theta and this is 2 theta. That's the central maxima. So what I should do, I know this formula. What formula? This theta formula. You said A theta was equal to n lambda. This is what we knew. Then theta is equal to lambda n lambda by A. We knew this. But for the central maxima, this one, okay, this happens where the dark spot happens when n is equal to 1, right? When the path difference is 1 lambda, this is where it happens. So n is 1. So this theta is actually lambda by A because n is 1 for the central maximum. And what is the width? What is the angle of the central maximum? It's 2 theta. So the angle, I'll say phi, is actually 2 theta. So it's 2 lambda by A. So you're going to have an angle of 2 lambda by A for the central maximum. But within this, you need to accommodate 10 double slit fringes. Then I have to find the angle of this one bandwidth. Well, I can figure it out, right? So if I do this, or I can do it like this, I'll use a different color in this itself. Something like this. So this is going to be my theta D. It's double slit. That is, phi is for the single slit, and this theta D is for double slit. This is what it is. But what do you know? You know that this is the bandwidth, and you know this is D. This is capital D, right? So this is capital D. This is capital D. So what is beta? Beta can be written as T into theta, right? Or theta D. You remember that formula S is equal to R theta formula. From that formula, I am writing this beta as D to theta. So what is theta D then? Theta D must be equal to beta by D. But what is beta? Beta from from double slit experiment is given by lambda D by D. So if I equate this, then beta so this beta is equal to this. Then theta D is equal to beta by D. Then D cancels, and I get lambda by D. So that is this theta. So likewise, I'll have 10 thetas, right? There are 10 of them, 1 theta, 10 of them. So that 10 theta D must be equal to this fact, this 2 theta, this one. So what do you do? Next one is 10 theta D must be equal to phi, which is equal to 2 theta. So 10 into theta D is lambda by D, and 2 theta is 2 lambda by E. So this become phi. So what is A? A is the width of the slit. That's what you want. So A, lambda will also cancel. So A will be D by 5. So what is D? D is given 1 into 10 power minus 3 will be 5. So this is 1 millimeter by 5, so this will give you 0.2 millimeters. So in the double slit experiment, if the width of the slit is 0.2 millimeter, then you will have 10 double slit bandwidths in the central maximum. When we did the double slit experiment, we didn't think about the slit width. We talked about D. D is the separation between the slits. We didn't talk about the slit width. But what we know, if we close at one slit, and then if we just allow light to pass through the other slit, then the slit will have a width, and then it will form a central maximum, and then other maximum. And then if you close this slit, and then if you allow light to pass through, then again that will form a central maximum and other things. Now if you open both, then they will superimpose, they will form a double slit pattern. And for you to have 10 double slit patterns in this, the central maximum, this condition should be satisfied. 10 theta d must be equal to 2 theta or 5. Then A should be 0.2 millimeter. The width of the slit, which we didn't talk about in the double slit experiment, which we can find with the diffraction part of this lesson. So if you have each slit with 0.2 millimeter width, and if they are separated by 1 millimeter, and if you have a screen at 1 meter, then I will have a double slit pattern with a bandwidth of 0.5 millimeter, and 10 of those bands will be in the center. So that's what I get to understand from this. Hope this is clear to you.